I, before I talk about approximation of integrals, I'm going to go over one problems, which is it's about integrals of this type. For example, x minus x plus 4 here, x squared plus 2x plus 5, and dx. Okay, and this is pretty in general form. Okay, it's it is in general form. Now, first thing we have to do is try to rewrite this in the simplest form. Okay, and right now you have x squared plus 2x plus 5, right? So you first make it like a square plus a constant. So what they're going to do is x squared plus 2x plus 1. Okay, then what section? Chapter 10? No, this is lesson 10. Sorry. This is a section. I typed it wrong. This is a section. I think it's 7.7. All right. So this will be plus 4, right? So 1 plus 4 is 5. So then this first three terms will be x squared, x plus 1 squared plus 4, okay? So you can use a substitution so that you can make it like 1 square u squared plus 1. So maybe we can do it directly. So x plus 1, if it's a 2u, right? Then use 2u squared is 4 times u squared and have a common factor 4. Okay, so that's my suggestion. So you will get du 2du equals dx. Okay, so let's change. This is going to be, let me write down that first. And you know why we have to use this substitution? It's better just one step, okay? That will be, here will be 2u squared and plus 4. Now what is x? X plus 4, x plus 4, x is 2u minus 1, right? X is 2u minus 1, so plus 4 is 2u minus 1 plus 4. That is going to be, right, 2u plus 3. Okay, dx is just du. Dx is 2du, sorry. 2du, right? And that's it. So you will get 2u plus 3, and here's a 4u squared plus 4, and here I have a 2du, right? So let's continue to simplify. Okay, so you will get separate, right? So you can take a 4 out, okay? So this is the integral 4 u squared plus 1, and here's a 4u plus 6, right? Du, right? Then you separate, it's going to be u squared plus 1 du, and here 6 over 4, that would be 3 over 2. Okay, and you know how to evaluate each of the integrals, right? So the first one is just natural log u squared plus 1, but you have to divide by 2. Now you can use a substitution game to get that. The second one is just arctangent u. Okay, then you replace u by x plus 1 divided by 2, then you solve the problem. Okay. Yeah, because it's our substitution, so u is going to be x plus 1 divided by 2. So that's it. So this will be the answer. Okay. if unless you are asked to use a table of integrals to evaluate integral, otherwise you cannot just write an answer without any details from in the middle. Okay, so you cannot just say I know this answer, put it there. Now, like this one, yeah, you may just put the answer there. Otherwise, if you don't see it, then you have to use a substitution again. W equals u squared plus 1. Then dw equals 2u du. So that's what you have. U times du is half of dw, right? And that's w. So then you have a half of the nature of w plus constant. Then you replace w by u squared. So I skip a little bit. I skip a few couple steps because this all I remember that. Okay, it's not from table of integrals. All right, it's not from table. Sometimes you can, just by guessing trying because there's u squared plus 1 and there's a u on the top, right? Okay, and if you still have a time, have a little bit of space, you can put additional note here why this is going to be half of the nature of u squared plus 1. Okay. This is a basic formula in the book. You can use it. Right. This section 7.7 is about approximation of integrals. Now, why we have to study the approximation of integral? Well, there are several purposes here. One is understand the definition of the integral. Okay, what's it mean, right? What does that mean? And second, you can understand the program behind this, behind to compute, approximate the integrals. When you use a Maple or Mathematica, those are the mathematical programs to do the estimate of integrals. They need some kind of formulas, okay, to approximate the integrals. Right. So this is the consider function be a function, right, defined on the interval from a to b that's closed, right? Now, what is the definition of integral? The definition of integral is as follows. First of all, you consider a partition. Okay, you divide the whole line. Suppose the function is above, right? The x-axis. Okay, so this is the first point A. That's the last point B. Okay, you divide this whole interval into many subintervals and not necessarily equal size. Then, our original motivation is trying to approximate the area of this region under the curve. So this is the point, for example, xi minus 1, this is the xi. And then take an arbitrary point here inside. This is called xi star. Okay. Then you look at the height of this point. Then you consider the area of this rectangle. The area of this rectangle is going to be fxi star times delta xi. Delta xi is the size of this interval. So delta xi is going to be xi minus 1. Okay. So this product is, if the function is positive, this product is going to be the area of that rectangle. Now, if the function is negative, then this will be the negative area. Okay, negative, if the graph is below the axis, then this will be the negative of the area of that region, okay, between the x-axis and the curve. Right, then add them together. This is a good approximation of the area of that region, right? Okay, and the integral, this is an approximation of the area. And the graph y equals f of x. Okay, we're assuming f of x here is positive. Okay, to make it easier, it's simpler. Yeah. All right. So so if you want to estimate, if you want to find the area, you just take the limit. Okay, right? So the area is going to be the limit of this above the sum. Okay, so in general, if the function is not necessarily positive, then the integral is actually is a limit of those sums. Okay, regardless of the partition, as long as the size of the subinterval, I think the approaches zero. Okay. Okay. If the size of intervals, those subintervals are getting smaller and smaller, and those numbers you're going to get, okay, approaches the same number, then that number, right, is denoted by this integral symbol. Okay, and it is called the integral of the function of the interval. Now, if f of x is positive on the interval, then the integral of this function is just equal to the area, okay, of the region, and the graph y equals f of x. Otherwise, the geometric meaning of this integral is going to be, in general, okay, the integral of this function is a total signed area. Okay, we call the signed area, not necessarily positive. Okay, it's a signed area between, I don't say and, between y equals f of x and the x-axis. Okay, and the x-axis. So how do you understand that? For example, this is a, okay, and here's A, here's a B, right? So there are, between the curve and the x-axis, there are three regions. One is above the x-axis, right? So we use a yellow, okay? So this is yellow. And the other one is below the axis. I've used a different color. This is below the axis. So there are three regions, okay, between the curve and x-axis. Now, if the area of each region is always positive, A1 denoted by A1, A2, A3, then this integral of this function is going to be A1, but the second one should minus, it's a sign, right? plus A3, right? Yeah, each capital AR denotes the area, which is a positive, okay, number of the region between the x-axis and the curve. Then the integral is going to be the signed area, okay, which means just the sum of the areas of the regions with a sign. Okay, if it's below the region below the axis, it's negative. Anyway, we can always approximate, because the integral is a limit, right? So it's always approximated by those sums, okay? Now, this is called the Riemann sum. Actually, Riemann was the first person talk about the limit of those sums. Okay, he showed that. The question is, this is your definition. The question whether the limit exists, right? And the Riemann's contribution is he's a German mathematician. Riemann's contribution is if f of x is continuous on the interval, then it's guaranteed the limit exists, okay? or the integral is the limit, right? Exists. Okay. And Riemann, I think Riemann passed away at age 39, but his major contribution is a Riemannian geometry. If you type this words on Google, you will see billions, not millions of web pages about that. It's not just hundreds, right? And without his theory, and Albert Einstein cannot describe his relativity theory, cannot describe the general relativity theory. This is a mathematics. It's not a science, but that's a language you can use it in every subject. Okay. So data analysis, for example, statistics, and the search engine. Oh, right? Without mathematics, you cannot do nothing. And the robot, right? So if you learn, if you understand more in a different area, you can use that into the interdisciplinary area. Okay. So some people even begin with the computer science and switch to the other area later and find out can make a great contribution just because you have more knowledge. So if you want to study computer science, you only focus on computer science, all those major courses, you probably not going to do well. Okay. Okay. If you learn lots of mathematics, probably can even do better. Okay. Yeah, there are lots of people like that. Okay. For example, I think there was a professor in the electronic engineering. His last name is King. Okay. And yeah, he has a PhD in mathematics. He never got a PhD in electronic engineering, but he can solve lots of problems in electronic engineering. Okay. Even there was a professor in computer science, and he has a master's degree in geometry, so he can use that knowledge to study imaging process problems. Other people cannot do that, okay, without the strong background in mathematics. All right, so let's continue. So the question is, yeah, so Riemann says guarantee you can use those sums to approximate the limit, okay, because the limit exists. Now, how do we, yeah, so we try to approximate there. So the simplest way to do is we use the, we don't want to take arbitrary partition, okay? We consider a special partition, which is such that xi minus xi minus 1, this will be just delta x, okay? It's a fixed, independent of that. Okay, delta x is going to be the length, the whole length of the interval divided by n. Okay, so you want to divide this interval into subintervals of equal size. So the length of each subinterval will be b minus m divided by n. So how can x0 is a, right? How can I write x1? Well, x1 is a plus delta x, right? And so on. xi is going to be a plus I delta x. Okay. Okay, so this is a right endpoint. So the right endpoint. Now you can also choose. Yeah, the first one is if you choose. Yeah, this is our fixed partition. If you choose xi to be the point in the subinterval to be the right endpoint, so this is a right endpoint. Okay. Then the Riemann sum, the corresponding Riemann sum. Yeah, this integral can be approximated by this. Okay. And delta x is same delta x. just B minus L over N. Okay, first of all, we affix a special partition. Divide the whole interval into n subintervals. Okay. Then I look at the picture. I find out that maybe there's other better choice, because if you look at, this one maybe you can sometimes overestimate or underestimate the region. If you look at the picture, if it's a graph, is increasing, then what if you use this is the xi, right? Xi minus 1 xi. If you use this point, so you actually add the area of this kind of rectangles together. So in this case, if the function is increasing, this will overestimate, the Riemann sum will be overestimate the area, right? Because the rectangle covers the whole region. Now, if the function is decreasing, then this will be underestimate the area. But the limit is still is going to be the integral, okay? Just every term, every Riemann sum is underestimated the area, okay? If the function is decreasing, this is overestimate, okay? And this case, okay? Right, this is I just look at the ice interval, and this will be right because f of xi is this height. So the product is the area of this rectangle, and this clearly is under the curve. So in this case, overestimate, right? Underestimate, I should call it. Underestimate, right? Of the area. Okay. So it's a good, it's still, this is a good approximation, okay, from the definition. And then someone will say, well, how about let's try the middle point? Middle point may be much better because especially for the function, especially for the function, and middle point I usually denote by x bar, okay, xi bar. So for the middle point, it's much better approximation because for the decreasing function or for the increasing function, okay. Why? Look at the picture here. Right, even this picture, right? This is the xi minus 1 xi. So the middle point is here, you see? I think the middle point is better in this particular case, right? So the area of this rectangle is almost equal to the area of this region and that curve, okay? So then this is going to be f xi bar delta x. Okay, this is called the middle point rule. Okay, the one on the top is called right end point rule. Okay. Then let's continue. Okay, we're trying to list all the possible ways to approximate integral. Okay, and the third one. Well, let's take a look at the picture again. Instead of choosing a point, okay, this is I interval, right? The IC interval. Instead of choosing a point, I'm going to just look at this is a trapezoid, okay? This is a trapezoid. Connect those 2 points by a strict line. I think it probably is even better, right? Guys, this is a trapezoid. What is the area of the trapezoid? The area of the trapezoid, okay, I hope you still remember that, is going to be the average value of the two sides, okay? And we use the area idea, okay, instead of, choose a point in the middle, okay, somewhere. And then multiply by the height. Height is delta x. So that is going to be that is going to be the area trapezoid. So I believe that, okay, this is going to be also a good approximation. And why this is true, first of all, okay? Why this is true? This is if you view the integral as an area, and the function is above the axis, and I'm pretty sure the sum of those areas is trapezoid. It is a very good approximation of the area of the region, but it's not obvious in mathematics why this would be a good approximation. Why this limit on the left-hand side, on right-hand side is going to be the integral, the same integral. So let me explain to you for this one, so it'll be easier to explain. So here's right, I separate, and it's divided by 2 delta x, and plus 1/2 I from 1 f of xi delta x. This is we use a left endpoint. Right? We use a left endpoint. Here we use a right endpoint. Doesn't matter, because the point is, as long as xi star, yeah, in this case, you choose xi star to be the left endpoint. In this case, you choose a point in the subinterval to be the right endpoint. But Riemann already proved that if the function is continuous, this approaches the integral of the function. Okay, this approaches the integral of the function, same integral. So add them together. This is add them together. This is just the integral of the function. Okay, that is why the sum of the area of the trapezoid approximate the area the area of the graph under the region. Area of the region under the graph. Okay. Right. So you can use a trapezoid to estimate the integral. Okay. Then later on, Simpson find out, well, we can do the better estimate. Okay. Trapezoid is just we approximate the curve using strict line, right? Because look at the picture here, right? We use a strict line between those 2 points. Between 2 points, there's a unique line passing through, and use this line to approximate that curve. And use a line, you can calculate the area under the line, and that is the area of the trapezoid. So how can we use a better curve to approximate this, or it is a given curve? And I think use a quadratic function. Okay, but I'm not going to give a proof. But what I want to show you is the following fact. Okay. Okay. So if you have take 3 points. Okay. Each of them, here's the h. Okay. The distance. So those are the 3 points, have the different height, y0, y1, y2. Now, there's a unique, given 2 points, there's a unique line passing through. Given 3 points, there's a unique quadratic parabola. There's a unique parabola actually. Y equals ax squared plus bx plus c. There's a unique parabola passing through those 3 points. Okay. Then, you can determine the ABC, okay, for a given y0, y1, y2. Okay. And this is going to be x0 and x1, x2 for you. Yeah. So using those sort of data, you can determine ABC. I'm not going to find the formula for ABC. What I'm trying to do is just find the area of that region. So the area of that region is going to be, okay, is going to be h over 3, okay, y0 plus 4y1 plus y2, okay. That's surprise, yeah. This is a this is actually a good exercise, you know. You can do it by yourself, but it's giving the book. Okay. So if this is a parabola passing through those 3 points and with the height y0, y1, y2, and then I can, yeah, then the area of that region is going to approximate, is given by this formula. All right. Now, what I'm going to do, I'm going to divide, yeah, consider, I'm going to use that to find another good formula, expression for the integral, okay? So what I'm going to do here is, this is A, this is a B, okay? I divide the, yeah, this is the x1, you know, x2, x3, x4, right? So delta x is going to be xi minus 1, x, so xi minus xi minus 1. Okay. All right. So right now I'm going to use a pair of those. Okay, and then just keep it going. So here it's y0, y1, y2, y3, y4, right? And you have 3 points. I'm going to approximate them by quadratic, by parabola. Okay, by parabola. This is probably, it's not it does not match with the original curve, but it's pretty good approximation. Then I write the formula for the area for each region determined by the parabola. Okay. So so the first one is according to, yeah, my delta H is going to be delta x, so 1/3 delta x. Okay. y0 plus y1, 4y1 plus y2. And then the second one is y2 plus 4 y3 y4, right? And keep it going. This should be going to be the good approximation of the integral. Okay, this was yeah, this was discovered by, introduced by Simpson. Yes. You know, everybody watched the Simpsons movies, right? This is not Simpson. All right, so the question is, how can I, yeah, the last one, I think n must be even, right? Because you know, you get a pair of subintervals. So this should be equal to xn. This is x0. So n must be even. Otherwise, I have a one additional at the end. Okay, n must be even. Okay. And but if you put them together, you will see that begins with y1, right? Then you have 4y, then y0, 4y1, but I think you have double y2. Then have 4y3, and you have double y4, and keep it going, okay? And the last one is y to the n minus 1 and yn, okay? So those are the terms. Now, what is yi? Yi is just f of xi, okay? That is the height of the graph. So this is a simple thing, right? That's all we need, okay, to know about. We have how many? We use a right endpoint. We use the right endpoints or left endpoints to approximate the integral. We use a midpoint to approximate integrals. We use the trapezoid to approximate the integrals. We can use we can use a simplest rule. Now, how do you know this sum approaches the integral? Can we prove that? I think you can prove that. Okay, it's not a trivial, and but one still can prove it. Okay. Okay. Okay, I'm not going to show you why the limit of the we call the the special sum. Okay, is going to be the integral. The question, yeah, this is an approximation. Okay, it's not that complicated to prove. Yeah, think about that. This is the limit must be also be integral. I'm not going to spend time on this. I'll give you a proof for the trapezoid. Okay, so let's take a look at the example. To evaluate this integral of e to the x squared dx. Now, we cannot find antiderivative of this function. No way. Okay, you cannot. You know the integral exists. Okay, but you cannot get exact value in terms of like x square root, of 2, for example. So the only thing we can do is try to approximate it. Okay, if you use a computer can do much faster computation. So you can choose as many points as you want. Okay, so this is the work. But here we only divide it into 1, 2, 3, 4 parts. Okay, so I'm going to let n to be 4. So delta x is going to be 1 minus 0 over 4, which is 1/4. Okay, so what is my x0? x0 is 0, x1 is 1/4, x2 is 2 over 4, x3 is 3 over 4, x4 is going to be 4 over 4, which is 1. Okay. All right. First, let me try to use a midpoint. Okay, the midpoint rule. Okay, using the midpoint is midpoint. So let's figure out the midpoint. Right, x1 bar, x2 bar, x3 bar, x4 bar. Right. It's easy to find the coordinate of each midpoint. Right, so midpoint x1 bar is going to be, I think it's 1 over 8. X2 bar, the gap is 1/4, so it's 3 over 8. X3 bar, 5 over 8. X4 bar is going to be 7 over 8. Okay, so those are the coordinates of the midpoint. Then the integral is approximated by delta x, right? Delta x and f of x1 bar, f of x2 bar, f of x3 bar, f of x4 bar. Okay, so let's put the details. What is delta x? 1/4. x1 bar, x is 1 over 8, so it's 1 over 8 square. 1 over 3 over 8 square. Okay, e to the 5 over 8 square. e to the 7 over 8 squared. So that's what they get. Okay. Yeah, we don't want the estimate. You can use a scientific calculator, not the graphing calculator. You can estimate this number. Okay. Okay. Now, if we want to use a trapezoid, yeah, we call it trapezoidal rule. Okay. And the expression will be slightly different. Okay. So in this case, I remember this is going to be delta x over 2, right? And f of use, not using middle point, actually we're using the point, yeah, twice of x3 and f of x4. Okay. Yeah, when you do the exercise, you write down this first. Then you plug in the number, okay? Delta x is 1/4, so it's a 1 over 8. And then this is e to the 0 square, twice e to the quarter square, and twice of e to the 3/4 square, and twice of e to the 3/4 square, and then e to the 1 square. All right. If we are able to estimate this should be much better estimated than the middle point. Right, then the middle point. And what is, yeah, what we can get from Simpson's rule? Okay, Simpson's rule. Simpson's rule. Okay, Simpson's rule. We have 4 numbers here, right? So you wrote and you gave you put the delta x over 3, and the first step we have to write down all the terms. Okay, then you replace f by the specific function. So the first one is x0, and 4x f of x1, and twice of f of x2, and 4 f of x3, and that's it. Okay. So delta x is 1 over 4, so it's 1 over 12. Okay, you write down all the numbers. Okay. Now, the expression of those sums are quite different. But if you use a calculator to estimate those above 3 sums, they are very close to each other. Okay, and you will see that Simpson's rule gives you the better estimate. Okay, gives you the better estimate. Okay. Okay, so those are the approximations of the integrals. Yeah, I'm not sure we have. I'm trying to do some comparison to which one is better. I did not use a scientific calculator to complete this. Okay, let's see what we can get. Yeah, all we need is just write all the terms explicitly. And let me show you one more example, right? For the quiz. Okay. So here's another example. Yeah, AST made the integral from 1 to 2, and 1 over natural log of x dx. No, this natural log of x. Okay. Natural log of 1 is not defined. Okay. Now I know you can evaluate this integral, but we're trying to estimate. Okay, using any of this, right? Then let's use the trapezoid method. Okay. So this case, delta x, yeah, let n to be 4. So delta x is going to be 2 minus 1 over 4, which is still quarter, right? Then x0 is 1, x1 is a 1 plus quarter, right? That'll be 5 over 4. X2 is 1 plus 2 delta x. So that'll be 3 over 2. X3 is 1 plus 3 over 4. It's 7 over 4. Then x4 is just equal to. Okay. So you write down all the numbers. Okay. Then we can use yeah, let me write down trapezoid rule. Okay. Now, if I ask you to use the trapezoid rule to approximate this integral, okay, what you should do is you write down all those. Write down x0, x1, x2, x3, x4 first. Okay. Then you write down the formula. Okay, this is going to be approximated by the delta x, right? You go back to here, you know. So here's a trapezoid, right? Delta x divided by 2 and all those numbers in the middle, right? So divided by 2, then f of x0 plus 2 f of x1 plus 2 f of x2 plus 2 f of x3 and f of x4, okay? So next step is to replace delta x, as this is 1 over 8, and f of 1, not 0, right? So it's natural log of 1 twice natural log x1 is 5 over 4, and twice natural log of 3 over 2, twice natural log of 7 over 4, and then natural log of 2. Okay. That's all. You know, you can we actually can combine them into one fractions. Okay, let's see. Natural log of 1 is 0. So that will be 4 over 5 squared, and then multiplied. Maybe I use yeah, I use a 6 over 4. It's the same, yeah. And then plus 7 over 4 squared, and then plus 2. And multiply by 2. Okay, right? Yeah. This is one number. You'll be surprised, right? Yeah. So this is a good approximation, and then to the s power. Okay. Then you can even simply write this a bigger number, right? Right, to the s power. Okay. But on the other hand, you see, remember, natural log of dx, right? By the integration by parts, this can be x times 1 over x dx, right? So actually it's going to be x natural log x minus x, okay? Minus x, when you differentiate, yeah, that's plus constant. So the integral from 1 to 2, in this case, you can evaluate. It is going to be, okay, then that's the first term, minus 1 natural log 1 minus 1. That's the second term. So natural log 1 is 0. Minus 1 is plus, minus 1 is plus 1. So it's 2 natural log 2 minus 1 plus 1 is minus 1. Right? Yeah. Yeah, that's right. So you can also write the natural log 2 square minus 1, right? And you can say natural log of 2 square divided by e, actually, because natural log of e equals 1, right? So this number should be almost equal to that number, okay? According to our approximation, okay? Surprise, right? So that's it. I stop here, so I'm gonna give a quiz. Okay. Yeah, when you do the exercise, I don't think you needed to approximate each of those terms using calculate. You don't need. All I needed to do is make sure all the terms correct, and the function should be. You cannot just put the f there. You have to replace f by the specific function you're given. Okay, and that's all. If you did it correct, yeah, all the terms are correct. Then we get 4 credits. Okay, after this quiz, we have a midterm, right?